Yes.
Just out of curiosity, what's the definition of superfluid in this instance?
It moves sort of without resistance. It doesn't have like viscosity to it. One of the notorious stories about superfluid helium is it will, like, if you put it in a beaker, it'll like crawl up out of the beaker. It's a very weird atomic state. So it's something that took them a long time to even get a good theory of it. It's kind of related to superconductivity, where atoms sort of couple in very long-range quantum effects. And I'm not that familiar with it. I've read a little bit about it, but I don't feel like it, that would be almost a whole other talk, and I'm certainly not prepared for that. Mm-hmm. But again, these forbidden lines are diagnostics used today for low-density plasmas. You don't stick your probe in there because it'll melt at very high temperatures. You look at the spectrum of the thing. You know what kinds of elements are in there, and you look at what excitation states they are at, and from that you can determine the temperature. This was in researching this stuff, this was one of the things that I stumbled across that was kind of the biggest surprise, because I didn't expect it. This is one of the problems when I was talking about spectra before. Double stars in the 1800s, when we identified them, very often we would see them, they would be in unusual color pairs. They would be, bright, contrasting color pairs. Alberio is one of the famous ones in the constellation Cygnus, which this is an image of. And here I just got just a simple graphic of just showing an example of the contrast. There would be often kind of a reddish star and a bluish star. And there was some question of, well, why does this seem to be so common? And well, one guy proposed in 1842 at the Bohemian Scientific Society, he put forth a paper that concerning the colored light of double stars and some other heavenly bodies. And the person who put forth this idea kind of surprised me, because we associate his name kind of differently. The gentleman was Johann Christian Doppler. Well, what was Doppler's proposal? Doppler's proposal was that double stars, they orbit around their common center of mass. One of the star is moving around this way, this star is moving around this way. So one of them is moving toward, at any given time, one is moving towards the observer. Let's say the observer at the Earth is over here somewhere. One of them is moving towards the Earth, and one of them is moving away from the Earth. And he said, oh, well, wait a minute. We now know that light is a wave. And so if light is a wave, then the star that's moving toward you will compress the oscillations of the wave so it's a shorter wavelength. And the one that's moving away from you will stretch out the wavelength. And so you'll see a bluish star will be the one that's coming toward you, and a reddish star is the one that's moving away from you. Certainly an interesting idea. It was a perfectly logical explanation that was completely wrong. Why? Well, you have to look at what other astronomers knew at that time. One, they were getting the first measurements of the velocity of light. This is in the mid-1800s. Romer's experiment had already been done. They had their first estimates of the velocity of light. Kepler's third law told us what these velocities had to be. We had a pretty good idea of what those could be. And we didn't have the first parallax measurements to other stars, but using the assumption that most stars were about the brightness of the sun, you could estimate the distance to them by just the 1 over r squared intensity law. So they had a rough idea of the distances. And it turned out that this would only work if these velocities were significant fractions of the speed of light. So it was just way too high. They knew this can't be right. But someone said, well, wait a minute, what about sound? Because it's a wave too. Well, and what must have been, I wish I could find an engraving of this that's public domain, because this sounds like it was really a funny experiment. Christoph Buys-Ballot in 1845 decides to test Doppler's idea by using sound. Basically, he has a bunch of horn players that can play a perfect tone. He gets them together on a train car, and then he has them play their perfect tone while the train car is moving by the station. And people listen for it. They listen to it as it comes in, they hear, oh, it's a higher pitch. As it moves by, it's a lower pitch. Pretty cool. So they had demonstrated that this trick could work for sound. Hippolyte Fizeau proposes in 1848 that this effect would probably work for light, and he talks about applications for spectral lines. Although remember, this is 1848. They don't yet know what's causing spectral lines. Early attempts to measure this effect for light prove incredibly difficult because it's a very tiny shift if you use the speed of light there. You need velocities of tens to hundreds of kilometers a second to get a perceptible shift. They finally get some success measuring the rotation of the sun and the radial velocities of distant stars. So the Doppler effect for light could not be tested except for objects in space. They were the only things that moved fast enough to make a detectable spectral shift. It was funny, in 1900, there was the guy that was responsible for a lot of these measurements had lamented about how, it's kind of a shame we haven't yet been able to do this Doppler effect in the laboratory yet. In 1900, someone managed to do it. They had another funny-looking contraption. It's one of these things you need to watch some of these old science shows. Sometimes they might show these things, where he shot a beam of light and had it reflect many times to measure the shift. He sent a spectral line through, and then he would move the mirrors out so that the velocity would be multiplied by the motion of the mirrors. And he got high enough speeds to get a detectable Doppler shift. But it took a few years, 11 years essentially, before they could measure it in a laboratory setting. Of course, today we have this instrument on board SOHO that takes full disk, what we call Dopplergrams of the sun many times per day. Well, it's about every 6 hours actually, where it measures the velocity of any point on the sun as to whether it's moving towards you or away from you. It gives you a velocity estimate. That's used for sort of doing like sounding measurements on the sun. The Doppler effect must be considered in many signal transmissions between distant objects. There was almost a serious mistake made in the Cassini mission because they found that as the Huygens probe was moving away from Cassini, the relative velocity might get high enough that it would move the signal transmission out of the reception range of the receiver, one of the receivers they needed to forward the signal. They managed to find a way around that problem, but I remember reading about that. Of course, there's loads of Earth-based applications for the Doppler principle, not just for light, but for sound. Doppler radar, LiDAR, medical imaging. Actually, a lot of things in radar, my understanding is that some of them don't actually use the shift of the wavelength of light. They send pulses out, timed pulses out, and then look at the change in the timing as the pulses return. Is done in a lot of cases.